Namaskar friends, I am Dr. Neeraj Upadhyay. In last few lectures, we dealt about crystal field theory and their applications on molecules possessing octahedral or related structure to octahedral arrangement. We learned in a crystal field of ligands of octahedral geometry, d orbitals directing towards the axis are repelled more than the d orbitals between the axes. A strong ligand field, high charge on central metal atom and larger size of the central metal prefer formation of low spin complexes, as in these cases crystal field splitting becomes larger than the pairing energy. Always a regular octahedral arrangement is not achieved. Sometimes there are distortion in octahedral arrangement because of unsymmetric filling of electrons in the Eg and T2g set of orbitals. The case when bonds of z axis is elongated than the bonds present in x and y axis because of presence of more electron in dz square orbital is called John-Taylor elongation. On the contrary, if the bonds present in x and y axis of octahedral arrangement are larger bond lengths of bonds in z axis, then the distortion is called John-Taylor contraction. Altogether, they are called John-Taylor distortion. All in the obtained distortion, Eg and T2g set of orbitals further split and form an entirely different crystal field arrangement. Square plane arrangement can be considered as a special case of John-Taylor elongation. But here, elongation is too large to hold the ligands from the z-axis. Since no ligands are coming from the z-axis, the orbital picture is entirely different. Now, in case of a square planar arrangement, only 4 ligands are approaching, but this arrangement is mostly done in presence of a strong ligand, and therefore the value of crystal field splitting here is high. In this lecture, we will discuss about approach of crystal field theory on the other arrangement of coordination number 4. This arrangement is called a tetrahedral arrangement. The learning objective of this module is to apply crystal field theory on tetrahedral arrangement of ligands around the metal and to find the cases when tetrahedral geometry will be preferred over a square planar or octahedral arrangement. A tetrahedral arrangement may be supposed to have been formed from a cube like a room where you are sitting. The center of the cube is the central of the tetrahedron at which the central metal ion is placed. 4 alternate corners of the cube are the 4 corners of tetrahedron which is shown in your screen. The 4 ligands are lying between the 3 axes x, y and z which pass through the center of 6 face of the cube and thus go through the center of the cube as depicted in the figure of your screen. The same kind of argument based on crystal field theory can be applied to these spaces as we used in octahedral arrangement. Assume the room in which you are sitting is cubical in shape and a ligand is placed in each alternate corner of the room. So, a total 4 ligands will be placed by this way. Also, assume metal is at the center of the room and ligands are bound with central metal ion. From the center, you can assume the 3 axes that are x, y and z axis. Now, imagine the situation. Are the 4 ligands on the axis? Answer is no, they are very far. Okay. Next question. Are the ligands exactly in between the 2 axes? Answer is no, not exactly. So, the last question. The ligands are nearest to the axis x, y and z or to the line between the axes that is x, y, y, z or zx. By careful thinking, you will reach to the conclusion that the ligands are near to the line between the axes. Now, generalize the concept. Let us suppose the 4 ligands which are lying in between the axes x, y, z are approaching towards the metal cation to form the complex. Now, since the lobes of T2 orbitals are lying between the axes, that is, are lying near to the path of ligands, these orbitals are experiencing greater force of repulsion from the ligands than those orbitals whose lobes are lying along the axis, that is, the e orbitals. Thus, the energy of T2 orbitals will be increased while that of e orbitals will be decreased compared to the barycenter. Consequently, the d orbitals are again split into two sets, T2 and E. However, the order of energy is reversed as seen in the case of octahedral arrangement. Energy calculation against barycenter would also be same as we have done in the module 7. That is, energy of E set will be decreased by 0.6 delta T and of T2 set increases by 0.4 delta T. Also, you can see in both set of orbitals T2 and E, we have not included the subscript G. This is because a tetrahedral geometry do not contain any center of symmetry. So, there is no point of considering Gerade and ungerade irrespective of the fact that the orbitals contain center of symmetry or not. Before filling the electrons to the splitted orbitals, let us address an important point that almost all tetrahedral complexes are high spin. Can you answer why almost all tetrahedral complexes are of high spin? There are only 4 ligands in the tetrahedral complex and hence the ligand field is roughly 2 by 3 of the octahedral field. The direction of ligand approach in tetrahedral complex does not coincide with the d orbital. This reduces the field by the factor 2 by 3. Therefore, delta T is roughly equal to 2 by 3 into 2 by 3 equal to 4 by 9 of delta O. As a result, all tetrahedral complexes are high spin since the delta T is normally smaller than the pairing energy. Hence, low spin configuration are rarely observed. Usually, if a very strong ligand field is present, a square planar geometry is favored. Now, let us talk about the crystal field stabilization energy of a dx configuration of the central metal ion in tetrahedral arrangement of ligands. We have seen that only high spin tetrahedral complexes are known in case of the tetrahedral complexes. The distribution of dx electron in E and T2 orbitals takes place according to the Hund's rule. The filling of electrons will start from E orbitals since these orbitals have lower energy than T2 orbitals. The energy gap between E and T2 orbitals in tetrahedral environment is denoted by delta T, which is equal to 0.45 delta O. Energy of E orbitals is lowered by 0.6 delta T, which is identical to 0.27 delta O, and that of T2 orbital is raised by 0.4 delta T, that is identical to 0.18 delta O relative to the energy of no splitting state. Now, let us consider a dx ion containing EP T2Q configuration in which P is the number of electrons present in E set and Q is the number of electrons present in T2 set and X is equal to P plus Q. CFSE for EP T2Q configuration is calculated by the formula minus 0.6 into P plus 0.4 into Q delta T. For example, in case of a D4 arrangement, the filling of electrons in a tetrahedral crystal field environment can be shown as in your screen. Since value of crystal field splitting for tetrahedral arrangement is always smaller than pairing energy, therefore, all 5 d orbitals even in split form will first singly filled, and then only pairing will start. It is obtained that two electrons are filled in each set of orbitals, each of which is stabilized by 0.6 delta t, and two electrons will be filled in T2 set of orbitals, each of which is destabilized by plus 0.4 delta t. So, according to the formula we have discussed earlier, CFSE should be equal to minus 0.6 into P plus 0.4 into Q that delta T, that it should be equal to minus 0.6 into 2 plus 0.4 into 2 delta T. This will become overall minus 0.4 delta T. Similarly, one can generalize the calculation method for determination of CFSE value for the configuration D1 to D10. Here in the table, we have already calculated the CFSE value for you and summarized on your screen. Now, applying the formula delta T equal to 4 by 9 delta O, we can calculate the CFSE value for all the configuration from D1 to D10 in terms of delta O, so that a true comparison with CFSE of the same configuration octahedral arrangement can be done. The fourth column in the table shown in your screen is the CFSE value in terms of delta O, but for tetrahedral arrangement obtained either by replacing delta T with 4 by 9 delta O by the formula CFSE for EP TTQ configuration in terms of delta T is equal to minus 0.6 into P plus 0.4 into Q delta T, which becomes minus 0.27 delta O into P plus 0.8 delta O into Q. Now, you can compare the value of CFSE obtained in tetrahedral arrangement of ligands with the CFSE value for electrons placed in high spin state of octahedral environment. I would suggest to please revise module 8 for calculating the value of CFSE in octahedral environment. So, you can see value of CFSE in tetrahedral arrangement compared to CFSE value in high spin complex of octahedral arrangement. The difference in CFSE for D0, D5 or D10 configuration for both the arrangement is 0. In D1 and D6 arrangement, the difference are small, that is 0.13 delta O. But difference in CFSE for D3, D4, D8 and D9 configuration in tetrahedral or octahedral arrangement is very high. It is also known that the value of CFSE in high spin state is lower than that of value of CFSE in low spin state. So, another valid question raised: if ligands have to be arranged around the metal ion and tetrahedral arrangement give less stability, then why at all a tetrahedral complex form? Here are some important cases where tetrahedral arrangement are preferred. If you have a bulkier ligand, it needs more space. Since the bond angles in tetrahedral geometry is 109 degree 28 minute, which is higher than the bond angle of octahedral or square planar arrangement. So, in case of bulkier ligand, tetrahedral arrangements are preferred. When ligands are weak, ligands try to minimize their repulsion by putting them far from each other. For example, if a complex have to be formed between a weak ligand and a metal ion having coordination number 4, the molecule will prefer tetrahedral arrangement over square planar arrangement, as loss of CFSE is less important compared to electronic repulsion between the ligands here. In general, with increase in oxidation state, value of crystal field splitting increases. But in the case metal has the low or zero oxidation state, molecule prefer to form tetrahedral arrangement over the square planar arrangement. If the electronic configuration is D0, D5 and D10, the value of CFSE is 0, and therefore formation of tetrahedral arrangement won't affect stability of the complex. Most of the complexes of these configuration prefer tetrahedral arrangement over square planar arrangement. Sometimes fulfillment of regular shape is important, especially when the electronic configuration becomes symmetrical in tetrahedral arrangement. The configuration D0, D2, D5, D7 and D10 in tetrahedral structure is regular. It is therefore D0 configuration like in TiCl4 and MnO4- has a splitting pattern E0T20, D2 configuration in FeO4 2- having electronic configuration in split state E2T20, D5 configuration like in FeCl4- having electronic configuration in tetrahedral environment as E2T23, D7 arrangement like in COCl4 2- have electronic configuration of CO2 plus in tetrahedral arrangement as E2T23, and a D10 configuration like in ZnCl4 2- have electronic configuration of Zn2 plus in tetrahedral arrangement as E4T26. Sometimes loss in CFSE is small when the molecule form tetrahedral arrangement. For example, CFSE for D1 or D6 configuration in tetrahedral arrangement is -0.27 delta O, and in octahedral arrangement value of CFSE is -0.4 delta O. Thus, formation of tetrahedral complexes give a loss of 0.13 delta O energy. Similarly, in case of D2 or D7 arrangement, the loss of CFSE is 0.27 delta O. Since the loss of CFSE is not much, molecules sometimes forms tetrahedral complex in these arrangements. According to crystal field theory, d orbital in tetrahedral environment splits into E and T2 set of orbitals. The E set of orbital accommodate dz square and dx square minus y square orbital which direct towards the axis, and T2 set orbital contains dxy, dyz and dzx orbitals. Since the ligands neither approach in the axial direction nor approaching exactly from the between the axis, the crystal field splitting in tetrahedral arrangement is lower than the splitting in octahedral geometry. Also, due to approach of 4 ligands instead of 6 of octahedral arrangement, value of crystal field splitting is lower in tetrahedral arrangement. By the relation delta T equal to 4/9 delta O, you can calculate or compare the energy difference in tetrahedral and octahedral crystal field splitting. Since ligands approach more closely from T2 orbitals, therefore, the tetrahedral field of splitting of T2 set of orbital are higher compared to E set of orbitals. As crystal field splitting in tetrahedral arrangement is lower compared to octahedral or square planar arrangement, stability gained by such splitting are also small. Even after getting low stability in tetrahedral arrangement, molecules arranged in this geometry mostly because of minimizing repulsion forces between the ligands, attainment of a regular geometry or of symmetrical electron filling. So, this was the explanation of crystal field theory for tetrahedral complexes. In next lecture, we will learn about applications of crystal field theory in explaining properties of complexes. Thank you very much for listening this lecture.